Hello, everyone. Welcome to this new episode of Echo this Friday. Welcome to all of you. You can let us know in the chat where you're joining us from. And today with me, I have my colleague Dan. Dan, are you joining us? Yes.
I'm here. I'm here. Hello. Hi, everyone. Yeah. How's everything going, Raphael? You well?
Good. How are you?
Yeah, very good. Thank you very much.
Yeah, so quite a few things this week. Right after KubeCon a few weeks ago, there was already the CFP for the next KubeCon in London in 6 months. This is a never-ending race.
Yeah, absolutely.
So the CFP for the main conference closed already, and this week it was for the co-located events, right?
Yeah, all the colo. So 10 different colo events, 2 more added, I think, for the upcoming KubeCon. They all finished up on Wednesday, I think, and we're getting close to the end of the year now. So there's only a few more events, I think, that you need to worry about.
Yeah, there's still one for this week, right?
Yes. This week, the final one is the State of OpenCon, I think it is, and you have 2 days left. So if you're excited about open source and you have some ideas about your journey in open source or what you're doing in open source, etc., you have 2 days left to submit to the State of OpenCon. But cool. Yeah, we're nearly there, nearly the end of the year.
Yeah, I think everyone is like wrapping up what they have to do for this year. Mm-hmm. Yeah.
Very much so.
So today you have a demo to show us.
Yes.
Implementing a service mesh from scratch with eBPF.
Yeah, I mean, we should probably kick things off a little bit with like kind of, I guess, explaining what a service mesh is. I mean, it's kind of funny because a service mesh is a different thing to different people. I mean, I went to KubeCon in 2017 when service meshes were kind of announced, and it was all anybody was talking about. And
how would you define it?
Oh, that's a good question. I mean, it's kind of weird because like the naming is a bit confusing because it doesn't necessarily need to do anything with services. It can be something else. But it kind of, to me, I think, especially when I first saw it, a lot of it was the demos that they were showing in 2017. You basically stuck this service mesh on, and all of a sudden you just had all these beautiful graphs showing you where all your traffic was going inside your cluster.
So like observability, service map.
Yeah, that sort of stuff. Yeah, you could kind of do that. And there was a lot of demos of kind of inserting traffic loss or doing, kind of blue-green canary deployments and stuff like that. Mm-hmm. And I think that's kind of what I first remember seeing service meshes kind of being demoed with. I think everybody was super excited because it was very, very visual. And then I think everybody kind of went home from KubeCon, deployed service meshes, and then kind of was like, well, I don't really have a need for it yet. And we kind of had like a year or two where like service meshes kind of were there, but nobody really kind of knew what they were going to use them for, I think, at that point. I think we've started to get there now.
Would you say service mesh is specific to layer 7, or like is Hubble, when you use Hubble for a service map, is that service mesh already or not?
That's a good question. I mean, Hubble is very clever in that it is not only looking at the traffic, it's also speaking to the API, and kind of it has the smarts to put 2 and 2 together and say that like not only is this just IPs and ports, it's a pod, and this IP belongs to a service, not another pod, and it can help you from that perspective. And I think a lot of the service meshes typically have largely been, just kind of ingesting the layer 7 data, and kind of a lot of it typically has been kind of HTTP stuff. and like we'll read the first bit of it. It's a GET request and this URL, and we'll take it from there and move traffic around.
A lot of mutual oath interest as well.
Yeah, so that's been a funny one, and that's kind of what I'm going to be demoing today. Actually, we're going to be doing some mutual auth, which it's a tricky one. I guess there's creating certificates on the fly. There's those certificates, and I'll cover this again, so I'm going to be repeating myself, but I do anyway. So, there's a bunch of information that you need about those certificates. You can't create them before the pod because you need the pod IP addresses or pod host names in those certificates so
it's on the fly.
But so you're in this position where the pod needs to be created so you can create the certificate, but then you need to apply it to the traffic and all that sort of stuff. So there's some real kind of funny chicken and egg stuff you need to kind of think about when kind of putting it all together.
I'm also thinking when I hear a lot of people talking about mutual oath, I think a lot of people think about essentially just checking a box like there is mutual oath between my workloads. But I've also heard people that actually use mutual oath so that they can retrieve the token and actually use it to authenticate applications directly in the application logic.
Yeah, I mean, it's not. There's a lot of that basically proving our identity, so ensuring that the traffic that we're receiving from this pod, not only is the traffic good, it's that we can guarantee that the source of this traffic, because the IPs are ephemeral and all this sort of stuff, we need to guarantee that we're actually speaking to the right person. Like somebody hasn't swapped things out or done something funny and redirected the traffic without that mutual I am who I say I am, and I can prove it because we all have the same CA and all that sort of stuff. And I think that's been kind of quite a big thing that people have really been kind of focusing on, is not only having encrypted traffic, but also the guarantee that who you're speaking to is who you're actually speaking to.
Yes.
Yep.
Which requires, in any case, a third party, right? It requires some kind of authority to guarantee.
Yeah. So, I mean, you can be your own authority. Nobody recommends that. I would definitely recommend not doing that sort of stuff. We will be doing that today because I don't have somebody else to authorize these sorts of things. So,
what I mean by this is that the pod itself cannot be the authority. There has to be an external authority, technically speaking.
Yes. Yeah. So again, a third party or something else needs to generate those certificates, and for both source and destination, based upon the actual certificate authority, and then they will exchange. They all came from the single source of truth, and then they will validate each other in order to then send traffic to one another.
Yes.
Yep.
And usually this is done using some form of layer 7 proxy. So Envoy is used very often.
Yes.
In most service meshes, because you need to analyze layer 7 traffic in order to do this.
Yeah, that's correct. Yeah. So I mean, Envoy is arguably the de facto, I think, in kind of having something that sits there in the middle. And yeah, I mean, Envoy, I was in a conversation the other day where somebody did a talk at KubeCon last year, I believe, where they were deploying Envoy everywhere, but they wrote their own control plane for it. I mean, Istio is effectively a control plane for Envoy. They were deploying Envoy everywhere, and then they wrote their own control plane, which would flip the switches and do the toggles on the Envoys and stuff like that. So I then went spelunking through Envoy's docs. I'm like, whoa, there's so many options to Envoy. Like, there's a heck of a lot you can do with it. So, like,
but that's also pretty much what we do in Cilium, right? In Cilium service mesh, we pretty much provide a new control plane to Envoy.
Yes, that's correct. Yeah,
based on standard Kubernetes resources like service and gateway API resources and ingress and so on.
Yeah, as I say, Envoy is pretty much the de facto way of funneling your traffic into this engine, which is Envoy, and that engine then will do what it needs to do with all the traffic it's receiving.
I think I saw a post. I think it was on LinkedIn or Blue Sky. I don't remember. This week actually about someone saying, "Hey, I looked at tons of service meshes, and they're essentially all doing the same thing, which is re-implementing a control plane on top of Envoy.
Yes.
Why can't we just agree on a common control plane on top of Envoy?"
Yeah, so annoyingly, somebody else did this post I saw as well. Like, we already have a standard for this, so I'm going to implement another one. And somebody has asked this question today. I'll bring this in. So, are we going to use Envoy or Istio in today's example? And we are not. I have written my own proxy and my own control plane. So there's no Envoy, there's no Istio. We're going to be re-implementing everything, like from the ground up today.
Cool. Yeah, I was going to show a few of the
comments
to say hi to a few people. So yeah, Sorab actually said hi. There's a little bee. Hussein as well sent a little bee.
Bring in the bees.
And we have Joseph joining us as well as Tony. So hi everyone. It's nice to have people here. And keep bringing the questions. There is a question from Hussein as well about the implementation. Do you also have an ext authorization filter implementation in your service mesh example?
No, everything is the example that we're going to be doing. Everything is pretty much internal. And as I said, this is a proof of concept that I put together. So, I mean, if you have ideas, feel free to raise a pull request or whatever. But we're largely kind of going to be stepping through this just to kind of understand, to a degree, how it all hangs together.
It does sound very interesting. I have this bag I got from KubeCon from Pyramid.io, and they have this thing which is the definition of I don't remember which way it is. I think it's authorization, and the definition is not authentication, or it's the other way.
Yeah.
just important again to remember the difference between authentication and authorization. And
yes,
even once you're authenticated, you still need to manage the proper authorization to the service.
Cool. Right, I guess we should probably kick off. So
let's get going.
I guess. So a couple of weeks ago, I wasn't at KubeCon, so I was basically sat at home with FOMO, and I saw it's all right, that happens. I saw kind of a lot of hopefully I'll get the next one. Yeah. I saw a lot of conversation that was kind of going on. There's some service mesh stuff that had been being announced, and there was kind of MTLS being talked about from some new features that were being added, and this, that, and the other. And I'm always fiddling with eBPF because that's generally what I do for a living, I suppose, these days. And I was like, MTLS and service meshes, like everybody talks about them and everybody uses them, but like, and we know that they have in the past been complex and almost too hard to use and things like that. So I was like, let's start from scratch. And let's see if I can build a service mesh from scratch. Let's see how far we can get. So, I think, if we look at most other service meshes, effectively, they will typically use IP tables to do traffic redirection and that sort of jazz. We will not be using IP tables. We will be using eBPF. So, that's the way we're going to be going with that. So, I think
there's a bit of a disclaimer here from Craig that this is dangerous path to take.
Yeah,
just to clarify as well, you mentioned MTLS. We talked about mutual authentication before. You're actually targeting MTLS in this case?
Yes. Yep. So,
like in the case of Cilium, for example, mutual authentication is not MTLS.
Yeah, so this will be doing authentication and MTLS in terms of encryption as well across from pod-to-pod traffic. Okay. So in terms of architecture, it follows a pretty much standard architecture. So we will have a proxy, we will have some eBPF, we will have a controller which will be doing two things. So I'll step in. The first part, arguably the hardest part, really is capturing the traffic and moving it somewhere else. And one of the key things about service meshes are you shouldn't have to modify your workload. that should be as transparent as
Should be
possible.
transparent, yes.
Yes. So the first thing that we need to do is basically hijack traffic and send it somewhere else. And in this case, it's our proxy. So yes and no, and I'll explain what that means in a second. We're delving into the proxy bit anyway. So effectively we need to capture that traffic. So eBPF has a ton of different ways of mutating traffic in an existing system. There's things like XDP, traffic control, and then there's sockets manipulation inside the kernel itself. Now, we're largely going to be focusing on egress. So we're going to basically be looking at a pod trying to speak to another pod. That's egress. Can't do that with XDP. XDP is only ingress. So that's out of the way. Traffic control is a bit of a nightmare because traffic control egress happens at the end of all of the IP table stuff. So application tries to speak, goes into net filter, IP tables, and we get the result of all of that, and then it's a bit of a mess, and it's hard to manipulate the traffic at that point. So
it's already been source netted.
It's already been mangled, typically. So what we need to do is we need to hook into where the application first tries to speak outbound. So we are hooking in to a C group hook called connect. So if you look at C code, there's a function called connect, which is where you make your first outbound connection to another host, and we hook into that, and that is where we start doing our mutating. So I'm going to bring in
all external communication will go through this.
Yes, yep. So let me bring up. It's time for some eBPF code, everyone. So we can see this. Let me make this a little bit bigger. I'll get rid of all of this. Right. So if I scroll up here, so this is where we hook in. We're hooking into Connect 4, which I know is a game, but this actually means Connect IPv4. I've only done IPv4 in this example. And quite simply, whenever a program is trying to do a syscall to do an outbound connection, so to try and connect to something, this code will be ran first. Quite simply, we'll make sure it's TCP. I haven't done UDP because I don't have all day. It's done TCP. It will get a configuration. So we have a map that we pass into the eBPF program. And that map has a few things in it, namely the PID of the proxy. And I'll explain why that's important in a second. But more importantly is the CIDR range for pod IPs. So we only care about pod-to-pod traffic here. So and
the proxy will be running as a local process on the same kernel.
Yes. Yep. So out of the config, so we get the destination address that we're looking for. We decipher the mask in there, and then we effectively, in this line here, will look at whether it is in the pod CIDR, and if it isn't, it will just return the traffic. Nice. I've just realized there's a lot of stuff commented out here because there's a lot of additional notes.
Yeah, that's right. So there's a question from Sora.
So yeah, the details. We're not really going to be copying. Well, so we're not going to be copying the entire packet. We'll be making a copy of its original destination, and I'll show you why that's important in a second. So we've not done anything yet. We've basically just made sure that this is going to where we expect it to be going, which is making sure that the IP address is part of the right network. And then this here is important. So this was a bit of a pain. Yes. So one of the things that we needed to do was to get the PID. Now, and I'll tell you why that's important, is because we don't want a proxy. We don't want this to run when the proxy is moving traffic around. Otherwise, we'll just end up in a loop where we capture traffic, send it to the proxy then should send it somewhere else. However, if we don't have this bit of code in here, the eBPF program will see the proxy's code and send it back to the proxy again, and code will not go anywhere.
Because the proxy is in the container network.
Yes, yeah. I found that out the hard way because basically all traffic just died immediately because
it was
just going around in a big circle.
I think CERN might be interested. They like hyperloops.
Yeah. So this is a function that I managed to find. So one of the problems that we have is there is a BPF get PID helper function. However, that will return the global PID, not the PID inside the container. Okay. So inside the container, this is normally going to be like PID 2 because there's usually just 2 processes in here or whatever. I'll get like PID 3000, which makes no sense, and I won't be able to see it. So we need to have a different way of being able to get the PID inside the correct namespace, which will get us the correct PID ID and we'll know not to do stuff. Why
do you need the PID? Oh, you need the PID of the process inside the container.
Yeah, so we send our proxy will get its own PID and then put that in the config, and it will send that to the eBPF program. Then whenever traffic is being detected, whenever there's a new connection, this bit of code will run and it will get the PID that is doing this initial connection. So the PID of the process that caused this hook to actually happen. We need to say, is the PID that is doing this connection the same as the proxy? But the PID that the proxy has is the PID of it inside the container. When eBPF tries to get the PID, it looks at the global PID map. It looks at the global PIDs for the entire system. So I'm 2, but it sees 3000 or whatever. So I need to get the PID inside the correct namespace, which is was a bit of a nightmare, but was doable. Okay. And then finally, so yeah, if it's the namespace PID and it matches the proxy PID, then we just ignore this traffic. This is to stop the kubelet checks from generally being annoying. We can kind of ignore this bit. This now is where it starts to get a bit more important. We get the cookie for the socket. So whenever a connection is established, a cookie is generated. And we store that cookie so that we can look up this connection later on. And we will then store the original destination and the original destination port in a map using that cookie as a lookup key. So we can then use this whenever we see stuff on the socket, we'll be able to get that cookie and we'll be able to find the original destination address and destination port. So we've now stored where it was going.
So you're essentially building a connection tracking map.
Yes, yeah. So we have that. And what we're going to do now is we're going to change the destination to our proxy, which is typically localhost. And then we'll change the destination port to our proxy port. So that connection now, instead of it going to pod 02, is actually going to be looped into localhost to our proxy address. And then we print out that bit of information, and that's it. So now, whenever a connection is established and it's pod-to-pod traffic, instead of that connection going to that pod, it's going to our proxy. And our proxy will then receive that traffic. So I'll quickly pop to the proxy code. The proxy code is quite simple-ish, he says.
Is that roughly what Cilium does when you have, for example, layer 7 network policies, where it actually evaluates layer 3, layer 4, and then sends the traffic into Envoy?
So I think typically and I'm not 100% sure. I don't know if any of the engineers are listening, so don't let me butcher this. But I think most of that's actually done through IP tables. I'm not sure if it's done through sockets at this point.
Interesting.
If I'm wrong, don't fire me. I'm sorry. I'm not 100% sure. Yeah, we'll find out. That's how we're doing it in this example anyway. We're effectively mutating a socket when we try and connect stuff. And then the proxy itself is just a simple Go binary. So this simple Go binary is, it does a couple of things. The first thing it does when it starts is, let me quickly, there's a lot of code we can kind of skip through here. It gets the PID. It sends that PID. It gets its own PID, sorry, and it puts that in the config. It will then load a bunch of our EB.
In which config?
One second.
Yeah.
Where's the PID bit in here? Oh, so we attach all of our eBPF programs. So we've got 3 eBPF programs. We saw the first one. I'll go through the other 2 in a second. So
the proxy actually interacts with eBPF.
Yeah, so the proxy loads eBPF, which does all of that traffic redirection. So we attach our eBPF programs through here. We then get all of the information that we care about. So we get the pod siders, we get the PID, and then the various other bits of information that we need. The proxy port that we're using, that is passed as we build this config, and then we update the map, so an eBPF map with that config information, so that eBPF can access that whenever a new connection actually happens.
This is the config that we saw in the C program before. Yes,
that's correct. Yeah. So PID, pod siders, ports, this, that, and the other, all sent at that point. And then we build our own TCP engine in here. So we have our internal listener, and this is where traffic is sent to. So when a new connection is established and we think it's going to pod 02, it's actually going to this internal listener. So that's listening on localhost, and that's where traffic will go to. At this point, we are getting all of the traffic from the pod. It doesn't know its traffic is going there. It's here where we can start to manipulate it. This is where service mesh actually kind of happens. So in the first iteration of when I was writing this, I basically would have 2 proxies, one sat next to pod 01, one sat next to pod 02. And effectively, I would capture traffic, and then I would just send it over to the second proxy, where I'd then send it on to the pod itself.
So like a very traditional service mesh approach with a sidecar, pretty much.
Yes, and just doing a simple tunnel. But one of the key things that we need here is that destination. So when we start receiving traffic, we're getting traffic from localhost and a high port number. How can I infer where this traffic was actually meant to go? And that is where, so I'll quickly step through the code here, but the listener starts, blah, 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 blah. It's listening. Oops, didn't need to look at that. Where's the bits I need here? Okay, so we've got the listeners, and there's internal traffic coming. So whenever a new connection occurs, so pod has tried to speak to something, it's been redirected to the proxy. That TCP connection has happened to us. We now have that, and we're now starting to understand the traffic. And
so whenever a pod sends an outward connection, it gets captured by the eBPF program and sent to the proxy.
Sent to the proxy, yeah.
And that's through the bridge interface of the proxy, or is the proxy listening on the host network?
It's listening on the pod's network. So it's sat inside the container. It's sat inside that net.
The IP of the proxy.
So it's all going to be local host at this point. I'll show you this, what it actually looks like from a network. But we've got a connection. We now have that. Before we start actually reading data from that TCP connection, what we need to do is work out where that traffic was originally going. And that's where this function comes in.
Based on the cookie, right?
Based on the cookie, yes. So what we do here is a syscall, which is get options on the socket itself. So this is a syscall called get sock opt, and this is all part of the Linux kernel itself. But effectively, there's a way of getting the socket's original destination before it was changed. This was added to the kernel eons ago for natting and things like that. But effectively, when we call that, our C code eBPF will actually interject. So here's us hooking into get socket options. And whenever we see that, where is it? That being called, we get the cookie. We look up in the map for the original destination and destination port, and then we set that and return that back. So inside here, we now get the original destination and the original destination port. So traffic is hitting the proxy. It looks like it's all internal inside the container. We need to work out where the next actual hop is.
Yes.
We've hooked into the socket options inside the kernel, and we've returned all of that. So now we have where that traffic was actually going.
This is done in user space, though, right?
So that was actually bridging into kernel space, and then eBPF actually interjecting in kernel space to do that map lookup based upon the cookie to tell us where our traffic was actually going. Does that make sense?
Okay, I'm not sure. The internal proxy function is running in user space, right?
The internal proxy runs in user space, yeah, and it's basically just doing a bunch of listening. So it loads eBPF, sets the config up for the eBPF, and then it basically sits and listens on a bunch of ports. One of those is the port where eBPF will forward all traffic to, and then
So the internal proxy sees the connection coming, and it sets up on the fly eBPF programs to manage this connection? No.
No. So on startup, an eBPF program is loaded.
Mm-hmm. On start of the proxy.
To do all of the traffic redirection.
Yes.
There are two other eBPF programs that are loaded. One which hooks into the kernel call for get socket options. Mm-hmm. So when we get the socket details, instead of the kernel returning what it thinks, we actually return the original destination to where it was actually going, because we stored that in a map based upon on the cookie itself. Mm-hmm. So we can now know the next hop where the traffic is actually going. So what we do next is we will build a MTLS connection to the destination address, but not the port that the application was on. We have our proxy running as a sidecar everywhere at this point. It will be sat listening on a different port, and I'll show you how this all looks in a second. Mm-hmm. But effectively, we will then connect to our opposing proxy. We will use MTLS for that connection, and we can see here it will send traffic to the endpoint gateway. So we'll load the certificates. We'll dial to the endpoint. So we've got that endpoint from that socket lookup, so we know where it's going. We connect to its endpoint. We create a TLS tunnel. We use MTLS as well, so that's why we have this here. So that's MTLS being enabled for it to actually ensure that it knows where the client certificates are coming from. And then it'll dial TLS over to the other proxy. And then the first thing it does is send over the original port that we were trying to connect to. Mm-hmm. And the reason why is because the proxy on the other end needs to know where it sends the traffic to once it starts receiving it. So at this point, end to end, our pod has tried to speak to pod 02. Our traffic has been redirected to the proxy. Our proxy then has looked up the original destination address and destination port. It's then connected to the destination address on a different port, the port of the proxy. It's then sent the original port that we wanted to connect to over. So now traffic has gone to the opposing proxy, and it then knows to do a connection to the original destination address and destination port, and traffic will then go to the application on pod 2. And that's the end-to-end connectivity.
So the proxy is not a layer 7 terminating proxy, it's a tunnel.
It can be. It is actually. It's layer 7. So we basically just down here, once we have the connections established, we're effectively just doing reads and writes from them. Because I'm just basically building a TLS tunnel on top of all of that. However, we can read all of that layer 7 data from these connections if we wanted to. I could do a read on it, and I could see it's HTTP and the get is this, at which point I could send the traffic somewhere else. I could basically infer all of that layer 7 information based upon how it's actually kind of going left to right, as it were. That's effectively end-to-end connectivity. I say eBPF will do the work of the IP tables. It will take care of taking that traffic and sending it to our proxy, and our proxy will do what it needs to do in order to get that traffic to somewhere else. So, I mean, all proxies are Istio, not Istio. Envoy is an overhead because it's doing packet processing. We're using Go. I did originally start writing this in C, but in the interest of time, it was much quicker to actually write this in Go. In terms of overhead, though, it's pretty minimal because we are setting up a TLS tunnel, and then as traffic is being read and written, we're basically just encrypting it and decrypting it in the same way your web browser is. There's not really too much overhead. In fact, most stuff is from an encryption perspective. Is offloaded to the CPU specific functions anyway. So it's you won't even see it in top basically if you're trying to work out what it's actually doing.
So the reason you wrote your own proxy is because Envoy doesn't have this logic of doing the lookups in eBPF to
no. So
traffic information.
Yeah. So there's a second part to this as well. So this is all using sidecars.
At this point,
yeah. So we put our sidecar in the pods that we care about, and whenever connections are established, we capture that traffic and we then do the communication between the two proxies, and then on the receiving end, the traffic is then forwarded onto the application itself. We can do what we want in that proxy now. I'm effectively setting up a TLS encryption between the two. We could read that data. We could put errors in there. We could infer it based upon HTTP routes or anything like that. But there's more to it at this point. So I say we've got the capability of building these tunnels. We need a way of getting our proxy in the pods. We need a way of minting certificates and things like that. So in order to do that, we have another program that we have, which I've imaginatively called the controller. That does two things. One, it will use an admission controller and it will add in the capability to watch for new pods being created. Before those pods are added to the API server, it will mutate them and add an init container, which is our proxy. And then it will also watch for pods.
Sorry, using init containers. I seem to remember that new versions of Kubernetes have a specification for sidecars now. Would that make sense?
They do, yeah. There's not really anything specific that's particularly helpful for what it is that we're trying to do.
Okay.
We effectively just need to have another container running in our pod, which has the proxy in there.
Okay.
And it's in the same net namespace. That's all it needs in order to capture that traffic.
Okay. Just wondering.
Yeah, that's fine. And I looked at ephemeral containers and things like that.
Mm-hmm.
It'd be kind of quite nice to be able to just attach at will. However, there's a big issue with ephemeral containers. And this issue is actually an issue on GitHub, and it's been open for like 2 years now. We need to get certificates into our pod because we need them in order to do the MTLS. Now, we can attach them through config maps, secrets, etc., or volumes and whatnot. you can't change the volumes once the pod has been created.
Mm-hmm.
So even with an ephemeral container, we can't add a new volume because that's part of the bit of the spec that can't be changed.
Yes.
So what we can do inside the spec of the container itself, we can do a secret map, which we do an environment variable. That is something you can do inside a spec, but it doesn't work in ephemeral containers. There's a bug, so it doesn't. It just doesn't work. So
and it works in normal containers.
Yes. So
as in the secret will be updated.
So we can do
or you just need the initial value.
Just the initial value.
Okay. Yeah. Then okay.
So yeah. So ephemeral containers basically the problem is that we can start an ephemeral container. We just can't get the certificates in it in any way, which basically renders this example
bad. Yeah, that's kind of defeating the purpose of this thing. Yeah.
Yeah. So as I say, the controller will basically watch for pods being created. When it sees a new pod that is about to be created, it will modify the pod spec, and it will add in an additional container, which is our proxy. And then it will then pass that to the API server for it to be scheduled. It also has another process which watches for pods. This process will watch for the update method. So whenever a pod is created, there'll be if you watch pod statuses, you'll see a pod add, and then there'll be a pod update. And the pod update is called when the pod has been scheduled and something has changed on it, like Cilium has applied an IP address to that pod. That's an update to the pod status. So we need to watch for changes to the pod. Once we have that IP address, we can then create a certificate for it. We can then apply that certificate. The pod will be able to look up that certificate, use those certificates, and then enable that communication. So that's how it works. And yeah, it's very small. Like I say, the overhead's kind of quite small. The proxy itself is 2 meg. That's the Go code and the eBPF program. So we're basically injecting a 2 meg container to our pod, and then the controller's a little bit bigger. That's the controller. There's only one of those anyway. So what I'll do is I'll bring up my terminal and we'll step through it all. And it's Fridays. We're doing demos. Hopefully it'll work. So let's see. So let me bring in my terminal. All right. So first things first, we need a cluster. So this will take a minute or so. So yeah, we're just building a kind cluster to demo this today. This is a proof of concept. Feel free to play with it. Don't put it in production. Don't expect me to support it if you do put it in production. Let's see where we are. Might take a second for everything to come up. Let me make this a little bit wider. Right, good. So everything looks happy. Everything is up. Right, so what I'm going to do first is I have put together a demo application, and the demo application is pretty straightforward. It's 2 pods and 2 headless services so that they can speak to one another. Quite simply, pod 1 will speak to the service pod 2, which pod 2 sits underneath. If we look at the logs...
So headless service, as in we talk directly to the pod. There's no access to your virtual IP address.
Yep. So, and this pod will create 2 connections. It will create a single TCP session where it's continuously saying hello, and then it will create a HTTP session where it's continuously creating a new connection, and you can see that because the port keeps changing, and it will just do a get to pod 2. And the reason why is I wanted to make sure in my code I could see new connections being generated all the time. So this, as I say, if we look at the manifest, it's a simple pod. pretty dull. There's the demo. And then we pass in what it should be connecting to. And as I mentioned, you've got two services, and they point to the pods that sit underneath them. So pretty straightforward. They just try and speak to each other. Right, let's delete that now.
Okay.
Because we're going to reapply this in a second. Right. So what we're going to do now is we're going to apply the controller. Cool.
And this controller needs special rights, I guess?
Yes. So it... so let me find the... So it needs the mutating webhook rights because it's hooking into that. And then it needs to watch for pods. And then it needs the capability to create and delete secrets.
Okay, but this is not going to inject eBPF, this part.
No, the proxy injects the eBPF.
Yes. So this only needs rights related to the API server.
Yes, yeah. So I say all this is doing is watching. And if it sees a pod being created, it'll modify the manifest. If it sees a pod being updated with an IP address, it will then create a certificate for that pod in its namespace with the correct name for it. So that's up and running. Now I'm going to do this wrong for a reason. So I'll reapply our demo.
So this is this whole system to create the certificates as soon as the pods are detected. And then they're updated with an IP address is to avoid typically the limitation in like Cilium service. In Cilium mutual authentication, for example, we wait for the first connection and then block it to create the certificate, right?
Yes, this I'll show you what happens with this. It's not as pretty as that, unfortunately. So if you see here, they still have one, and that is because I didn't apply the label. So in order to make sure that we don't go crazy with sidecars, I'll just delete this again. Label. So I've now added a label to the namespace where our pods are going to be created. And
so it's activated per namespace.
Yes, yeah. So now if I apply the demo, and that's fine. That's meant to look like that. If we look at the logs here, we can see here it has patched our manifests, and it's also created the secrets for pod 1.
Okay.
Wait, that bit bigger. So we've got these secrets that have been created. So one for pod 1 with Smesh for service mesh, and one for pod 2. And if I look at the pods now, there's now 2 of 2 as opposed to 1 of 1. We now have our proxy sitting inside that pod. So we made no change to the application. The application came up. We caught it in midair. We injected our proxy. Our proxy is doing what it needs to do. We've also created the certificates needed in order for end-to-end TLS to actually work.
And the secret is also injected in the specification of the pod.
Yes, yeah. So if we look at the get on minus O YAML.
I'm missing pod.
Oh,
I'm missing the type.
I feel it should be able to infer that, but never mind. So this is the pod IP that our CNI has given it. That's what we needed in order to create the certificate. Yes. But also, we will see in here. Where are we? Here we go. So this is our init container that's been added. Oops. So we can see here 3 secrets from the pod 01 have been added. And there's the proxy. That's actually up and running. And that's what it's added automatically to our container. And now, if this is all working okay, there we go. So this is the logs from the proxy itself. And if we go to the top There's a lot of connections already established. Here we go. So the proxy started. Let me make this a little bit wider. So the proxy started. It detected its own PID, which is PID 7. This
That's
is
the PID inside the pod.
That's a PID inside the pod, yeah. And that is passed to our eBPF program, so it knows not to loop itself. This is the address where all traffic is sent to by the eBPF program. And then these are, so this is unencrypted proxy-to-proxy traffic.
Okay.
And this is encrypted proxy-to-proxy traffic. So when we send traffic over these addresses, it's encrypted end-to-end. And we can start to see here the first connection. This is forwarded from eBPF. So this is pod 01 trying to speak to pod 02. The traffic has been redirected to our proxy. And we've done a lookup. We found the original address, which was here. That's what we've gotten from that get sock op. So we know where the traffic was meant to be going. We've now proxied it over to pod 02, but the address of its encrypted endpoint. So we've captured the traffic. We've created, we've used the certificates. We've created a TLS over to the other proxy. Traffic is gone. It's decrypted and then sent on to pod 2 where it's listening on the other end. And we've done all of that without any changes to the pods themselves. Everything's all automatically generated. eBPF is doing magical eBPF things. And we kind of have the beginnings of a service mesh.
That's very cool. What is the sidecar approach? Is this a restriction, or would there be a way to get rid of this actually?
So sidecars are the easiest way of doing it.
Yes.
It might be possible because of the way that I'm hooking into the kernel to have a singular process running per node that is seeing all connections. So I did start looking into doing something, and yeah, like
because at the moment you're attaching to localhost and the pod, right?
Yes, yeah. So we're attaching to we're exposing a port. We're doing a TLS listener. We're doing a TCP listener inside each port where we're redirecting all traffic to, and then we're doing a bunch of stuff.
This is actually the reason why you're looking for the local PID, because it's running in the same namespace.
Yes, yeah.
So it would have to be a totally different logic if it were a global proxy.
So yeah, we could. So what we can do is we can pass the name of the host itself to. So we would basically have something sitting in the host namespace. The problem with doing it outside of the pod is that CNIs will have been there and done their thing, and like it's the further you get down the chain, it's harder to work out where traffic should be going and whatnot. This will always work in this way, regardless of the CNI, because it's happening first before CNIs or other service meshes or anything else gets to do that.
Yeah, so Sorab is asking a similar question.
Same question, yeah.
Yeah, it's the same question.
So the answer is... I think so.
Go ahead.
I think so. I haven't had time. I mean, this I kind of managed to put together in a weekend. It was one of those weekends where my kid was away, and I was like, I've always wanted to have a go at doing this. So I basically managed to, hunker down and concentrate and manage to throw something together. And yeah, I think it might be possible to just have a single Smesh proxy. I'm not going to keep that name. I think it's quite terrible, but it's the first thing I came up with.
I like it.
Right. Well, I'm submitted to the CNCF then. But
is this approach you're using similar to other service mesh approaches?
Yeah, I think it's pretty similar to kind of like how Istio kind of used to work. You would have an init container that would basically hammer a bunch of IP tables rules into the pod, and then you would have another sidecar which would have Envoy in there.
Right.
So traffic
You're just
is then
essentially replacing the IP table logic with eBPF.
yeah. And our much smaller proxy, because it's really just quite simply moving traffic back and forth between workloads.
Mm-hmm. How does this compare to the approach used in Ambient? Do you know?
So, I mean, Ambient basically will funnel everything towards the Z tunnel, which is it's something we could do. We get your coding gloves on. It's something that could be done, I think. As I say, kind of like Saurabh's question, we could potentially just have no tunnel, and we could just have our eBPF and our singular controller as a daemon set, and potentially have that logic just in one place. Sadly, I've got a day job, and there's only so many hours in the day for me to see where we can get to with that. But I think it is possible. I just haven't had time to look at that. So maybe we could.
There was another question from Saurabh a little bit before.
Yes. So it's just on my GitHub page. So if you go to github.com, the BSD box /smesh, and on there I kind of documented the entire process. Actually, I'll just bring it up. Give me a second. Because I basically as I kind of worked out the various bits, we're almost out of time, so I'll quickly do this.
That's all right.
Share window. So yeah, this is the repo, and we can kind of see the original architecture. We basically have one pod trying to speak to another pod, and the CNI is doing magic in terms of getting, if that's node to node, getting traffic between A and B. So my 0.0.0.1 example is where we have eBPF capturing the socket, forwarding it to our listener, and our listener will send it over to the original destination, but just with a modified port. And then our other proxy will then forward that back onto pod 02, and that's the service mesh tunnel. That's kind of the eBPF details there. There's a bunch of issues that I had. Kubelet's a bit of a nightmare, continuously sending traffic and stuff like that. So we needed to kind of filter a lot of that out and getting the correct PID from the namespace and all that jazz. And then kind of the main one really that I wanted to do was kind of the TLS stuff. So that's where we needed to create a certificate on the fly as a pod comes up. We needed to get that pod, that certificate into our proxy and do that sort of stuff. And we can see in this bit here, if we use TCP dump, and if we're using Cilium, so if we do TCP dump on the Cilium VXLAN, so that's the tunnel that's built when nodes are speaking to one another, we can see instead of the plain text, which is hello from pod 01, we'll actually start to see it's just encrypted data. So we can see that encryption is actually taking place between the two. Even though there's no encryption in the application, we're taking care of doing that as part of our service mesh. And then this is basically version 0.0.3 is the thing that I showed today. We have the init container added. The watcher will watch for pod IP being populated and get you all of that sort of stuff. So that's kind of it, I think.
That's pretty cool. That was really great to go through the process.
Yeah, and it's
no pun
it's
intended.
Oh yeah, no, absolutely. We go through many processes, and that's it's good. Kind of almost cathartic to a certain degree to put together a service mesh in order to understand. Yeah, there's a lot of issues that you need to overcome to make a service mesh. Kind of minting certificates on the fly, making sure that you're only kind of touching the traffic that you're meant to be touching. Kind of doing all that sort of stuff. So it was a fun weekend project, and I hope it if it is potentially useful for other people who want to learn. It's out there. If you have ideas, feel free to have a play. But yeah.
Well, you're lucky. You live in Great Britain, so you have cloudy, rainy weekends.
Yeah. Well, we have a massive storm apparently coming this weekend. So
I'm looking forward to the next comments.
Yeah, who knows if I have time to make something this weekend. So
all right.
Yeah, cool. Cool.
Well,
Thank you very much.
That was super cool.
Yeah, cool. Awesome. I think that's it then, is it? I think we're ready to wrap up.
Yeah, it's full already.
Cool.
So
all right.
Fun experiment.
Awesome. Well, it's goodbye from me then.
Great end of day, great weekend. And
yeah.
See you later.
Bye, everyone. Thank you.
Bye.